What's happening, everyone? In this video, we'll be continuing our Python algorithm series by introducing the gram scan algorithm, an efficient approach for constructing convex hulls. In the beginning of this lesson, we'll briefly cover some background on convex hulls, and move over to the theory behind the gram scan algorithm. Towards the end, we'll open up our coding editor and implement the gram scan algorithm in Python, along with some test cases and visualizations to ensure our approach is valid. As always, throw me a thumbs up or drop a comment if you enjoy the video, and consider subscribing if you'd like to stay up to date on the rest of my Python coding content. So to start things off, before we can really talk about the gram scan algorithm, we need to understand what a convex hull is. As we can see on the slide, given a set of xy points, the convex hull is the smallest convex set that contains all the points. So essentially, if you're provided with a set of xy points and are asked to construct the convex hull, you need to return a subset of those points that's convex all the way around and contains every single point. For this lesson, I'm assuming you already know what convex means, but if not, there's actually a really simple way of checking to see if a shape is convex. What you do is start at any of the vertices of the shape, and work your way around the shape in counterclockwise order, from vertex to vertex. If you ever have to spin out clockwise to make it to the next vertex, then the shape is not convex, meaning it would be concave. So for the pentagon on the right, we know it to be convex because we never have to spin out clockwise if we traverse the vertices in a counterclockwise rotation. A way of visualizing a 2D convex hull, albeit more difficult to explain than to see in person, is the rubber band test. Basically, if you had access to a pegboard, like the one on the bottom right of the screen, and you inserted pegs at each of the locations of the XY points in your input, you could stretch a rubber band around the outside of the pegs, and it would automatically snap into the exact orientation of the convex hull for those exact data points. So for the example in the picture, there are 4 points contained inside the convex hull, the 3 touching the rubber band and the 4th in the center. Now that we have a rough idea of what a convex hull looks like, you may be wondering what they can be used for in the real world. A great example of a hot topic right now is object avoidance with self-driving cars, or any automated vehicle for that matter. Imagine your self-driving car is outfitted with a sensor that can only detect red taillights, or a crude camera that can only make out the edges of the cars in front of you. In either of these cases, if your car would like to make an informed decision, it needs to know the outer bounds on all vehicles surrounding it. For this purpose, the data gathered by the camera system can be fed into an algorithm to construct a convex hull, effectively turning the raw image data into precise outlines of all surrounding vehicles. As I'm sure you realize, this is simply one of many possible examples. Essentially, anytime we wish to distill information from a set of spatial, or even latent space data points, a convex hull may be of use. So now that we've covered some background on convex hulls and how they can be used in practice, we'll move into the main topic of this video, how they can be constructed. Even though this lesson is focusing on the gram scan, take note that there are numerous possible approaches to take if you encounter a need to create convex hulls in a real-world application. Obviously, each different approach comes with its own benefits and drawbacks. On this slide, we can see the average time complexities for some of the more popular approaches. When comparing convex hull algorithms, we evaluate efficiency using both the input size n, as well as the output hull size h. So for example, if you're working on a project where you have a large input size, but know that the final hull will only consist of a minimal number of data points, you may want to consider choosing an algorithm such as Chan's, which is sensitive to the final hull size. The idea to introduce gram scan was actually recommended to me by a viewer, John Kangaroo, and I really like the idea. Gram scan's competitive performance hinges mainly on its use of efficient sorting, and since we just finished up our sorting algorithm series, we should be able to carry over much of what we learned to improve our construction of convex hulls. So on a higher level, we've already covered what happens inside the gram scan algorithm. We take in a set of points and return a subset of those points constituting the points on the convex hull. On a lower level, we can break down the execution into 4 distinct phases. In the first step, we locate the point in the input set with the lowest y coordinate. If there are multiple points sharing the same lowest y coordinate, we choose the one with the lowest x coordinate. Here we'll call this point P. In our code, we'll use the word anchor because I think it more accurately describes what's going on. In the second step, we sort the remaining points in increasing order of polar angle to the point P. As you can see in the graphic, we can visualize this by plotting all the points with respect to P at the origin, and sweeping a line through counterclockwise. Starting at the positive x-axis, each point will be added to the list in the order as struck by the line. If there are any points with the same polar angle, we apply a secondary sort in order of increasing distance from P. After we've sorted the remaining points, we can start another list to hold the points on the convex hull, and initialize it with P as the first element, and the first element of the sorted list as the second. We then enter into the main loop of the gram scan, where we iterate over the remaining elements of the sorted list. For each element, we check to see if adding it to the current convex hull would result in a clockwise rotation with respect to the prior 2 elements. If it does result in a clockwise rotation, we know that something is wrong with our current hull, because recall, for a shape to be convex, the counterclockwise traversal of the vertices should never require a clockwise rotation. So we backtrack until adding this new point doesn't result in a clockwise rotation. When we say backtrack here, what we really mean is deleting the last element on the convex hull, and like we said, this is repeated until adding the new point results in a counterclockwise rather than a clockwise rotation. In the GIF on the bottom right, you can see the backtracking occur whenever a point is removed from the current convex hull. Once we're finished iterating over the sorted points, our hull list will contain only the elements present on the convex hull in order of increasing polar angle from P. Now that we've covered the steps involved in GramScan, we'll open up our coding editor and implement the algorithm in Python. So before we get to the actual GramScan function, we have several helper functions we'll have to cover first. To start with, we need some XY data points to work with, so for this purpose we'll be writing a function named createPoints. The first parameter to create points, count, will denote the number of data points we should create. For each data point, both the x and y coordinates are chosen randomly using the randInt function. We pass the randInt function the second and third parameters, min and max, so that all values lie in the same range, by default between 0 and 50. We'll now test the createPoints function by printing 10 random data points. The next function we'll be implementing, scatterplot, will be used to visualize both our data points as well as the convex hull. The function will be passed the data points as the first parameter, and optionally, the convex hull as the second. If the convex hull is not provided, its value will default to none, and will restrict our plot to just the data points. Inside the function, we'll begin by unzipping the data points into two separate lists, the first holding all x coordinates and the second all y coordinates. We'll then pass the x and y coordinate list to the matplotlib scatter function, which will create a 2D scatter plot of all the data points. We'll then check to see if we were passed a convex hull. If so, we'll iterate over the points in the convex hull, and add line segments to the scatter plot representing the boundary of the convex hull. We'll use an extra iteration at the end of the for loop to wrap the boundary back around to the anchor point. At the end, we'll call the show function of matplotlib to open up the plot to the user. We'll now test out the scatterplot function by passing it some random data points. The next couple functions we'll be implementing are short helper functions for the quicksort algorithm, which we'll be using inside of GramScan to sort the points by polar angle. The first method, polar angle, will, surprisingly, compute the polar angle in radians from P1, its second parameter, to P0. If a value isn't provided for P1, we'll set it equal to anchor. Anchor is a global variable which will be set inside of our GramScan function. Recall from earlier, the anchor point, or point P as we were referring to it, is the point with the lowest y coordinate in the input set. Since all our points are sorted by polar angle with respect to the anchor, we don't necessarily need to pass it to the function every single time. To actually compute the polar angle, we'll first calculate the distance between the 2 points in both the x and y direction, then pass those values into the arctangent function of the built-in math library. The logic behind this is fairly simple trigonometry. We have the length of the opposite and adjacent sides of a right triangle, so the easiest way to calculate the angle is using arctangent. The second helper function is an approximate Euclidean distance. I say approximate only because we don't take the square root, and we don't need to because we're just comparing relative values. Similar to polar angle, distance will be passed 2 points, P0 and P1, P1 again defaulting to our global variable anchor if it's not passed as input. Again, we'll calculate the x and y span, and this time, square both and return the sum. The last small helper function will be used to determine if a sequence of 3 points constitutes a clockwise, counterclockwise, or collinear turn. The function will be named det, short for determinant, a matrix function used to find, in this case, the signed area. All we really need to know is if the determinant is positive, the 3 points represent a counterclockwise turn. If it's negative, a clockwise turn. And if the determinant is 0, all 3 points are collinear, or in a straight line. Now that all the small helper functions are out of the way, all we have left are the GramScan function and our customized quicksort algorithm, used by GramScan to sort the points by polar angle. We'll start with the quicksort function. It'll basically be the same as the quicksort algorithm we coded up in the quicksort video, but with some minor changes to tailor it to our current requirements. The first change is, obviously when we select our random pivot, we need to calculate its polar angle from the anchor. In the same vein, when iterating over the points in the for loop, we'll require another call to the polar angle function so we can compare the polar angle of the current element to the polar angle of the pivot. Lastly, when stitching all three subarrays back together, we'll apply our secondary sort to the elements of the equal array so they appear in order of increasing distance from the anchor. Now that quicksort is complete, we finally set the stage to write the GramScan function. The function will be passed two parameters. The first is the set of data points we wish to construct a convex hull for, and the second, show progress, is a flag that if set to true, will cause us to plot out the convex hull on each iteration. So each time we add a new data point to the hull, we'll call the scatterplot function, passing the current hull as the second parameter, so we can see the progression as we add more points. Inside the function, first thing we'll be doing is declaring our global variable anchor. In Python, anytime you want to access a variable declared inside of a function, outside of it, you need to declare it as global, and this declaration should appear at the top of the function. Recall that we rely on the anchor variable inside both our polar angle and distance helper functions. The next thing we'll be doing is resolving the actual value of the anchor variable, the point with the lowest y-coordinate. To achieve this, we'll iterate over all points in the dataset, updating our min index variable whenever we find a point with the new smallest y-coordinate. If there are multiple points with the same lowest y-coordinate, we should choose the one with the smallest x-coordinate, and the logic for this is handled in the second if statement. At the end of the for loop, we'll update our global anchor variable with the point we've just found. Now that we've decided on our anchor, we can call the quicksort function to sort the points by increasing polar angle. After sorting, we'll delete our anchor point from the sorted list, so we don't accidentally add it to our hull twice. We'll then initiate the hull with its first two elements, the anchor, and the first element on the sorted list, aka the point with the smallest polar angle to the anchor. Because the convex hull will always contain the anchor and the first point in the sorted list, we'll add them in now so we don't need extra conditions in our next for loop. After we've initiated the hull, we'll iterate over the remaining points in the sorted list. For each point, we'll enter into a while loop where we continue backtracking until the addition of the new point doesn't result in a clockwise or linear rotation. Again, the backtracking is as simple as deleting the last element on the current hull and retesting for clocwiseness. After we delete the last element, I've also added in a check to ensure we don't accidentally delete our anchor point, but this isn't really required, so you likely don't need to add it into your own code. After the while loop, we'll append the current point onto the end of the hull list, and if show progress is true, we'll plot the points in the current convex hull. At the end of the function, we'll return our hull list, now containing all points in the convex hull in order of increasing polar angle from the anchor. Now that we've finished the algorithm, we'll write some simple code to test it out. We'll create a set of 10 data points and print them at the terminal. We'll then construct the convex hull and print it out as well. At the end, we'll call scatterplot to visualize the data points in the new convex hull. We'll now turn on the show progress flag for the GramScan function so we can see how it looks as the convex hull is slowly constructed. That brings us to the end of this video, everyone. I hope you enjoyed it and have a better grasp on convex hulls, and specifically the GramScan algorithm. As with most of my recent lessons, all the code we covered here can be found on my GitHub, so I'll drop a link in the description in case you missed anything, or were just watching for fun. Once again, I hope you found this video helpful, and I'll see you guys next time.